Today we are covering residual connections. Why deep networks keep signal across many layers. The goal is not to memorize a slogan. The goal is to build an interview-ready explanation that moves from intuition, to mechanics, to trade-offs, and then to a concrete example. Intuition. A residual connection gives a layer a shortcut path. Instead of forcing every layer to completely rewrite the representation, the model learns a change added on top of the existing signal. If you remember only one thing, remember the shape of the problem. Raw information is transformed into a representation that makes the next decision easier. Core mechanics. Residuals add layer output back to layer input. They improve gradient flow through deep networks. Layers can learn refinements instead of full transformations. They make very deep transformer stacks easier to train. They are usually paired with normalization. The compact mental model is output equals x plus sublayer x. Do not rush past the symbols. In an interview, define each part in plain language before you talk about implementation. That makes you sound like you understand the system, not like you only memorized notation. Common traps. Without residuals, deep networks can lose signal or train slowly. Residuals do not remove the need for normalization. Bad scaling can still make deep models unstable. Shortcut paths help optimization, not magic generalization. Concrete example. If a layer only needs to add information about a pronoun reference, residuals let it keep the original token representation and add the new feature rather than rebuilding everything. Walk through the example slowly. Say what changes at each step, what stays fixed, and why the operation helps the model produce a better representation. Interview checklist. Define the skip connection. Explain gradient flow. Intuition. Use refinement rather than rewrite. Mention pairing with layer norm. Connect to deep transformers. A strong final answer for residual connections should have 4 beats. First, give the intuition. Second, name the components. Third, describe the formula or data flow. Fourth, mention the trade-off. If you can add one example, you will usually sound much more practical than someone who only gives a textbook definition. Now let us rehearse the answer in a more conversational way. Start broad. What problem are we solving, and why did this idea become useful in modern AI systems? Then narrow down, what data structure or tensor is being manipulated? Then explain the operation. What is multiplied, normalized, added, masked, or learned? Finally, connect it to behavior, faster training, better context, more stable gradients, lower memory cost, or clearer generalization. For interview practice, avoid 3 mistakes. Do not give only math without intuition. Do not give only intuition without naming the mechanism. And do not pretend there is no trade-off. Most AI interview questions are really trade-off questions wearing a concept label. The best answer shows you know when the method works, when it becomes expensive, and how engineers usually manage that cost. Quick recap: residual connections. Why deep networks keep signal across many layers. Use the mental model, define the pieces, give the example, and close with the practical trade-off. That is the answer structure to keep in your head. One more interview rehearsal. Explain it as if teaching a teammate. Define the input, describe the transformation, name the output, and close with why the design choice matters in real systems. This habit turns a memorized answer into a practical engineering answer. Second rehearsal. If the interviewer asks for more depth, connect the idea to tensors and runtime behavior. What is stored in memory? Which dimension grows with sequence length, hidden size, or number of heads? Which part is learned, and which part is a fixed rule? These details separate a surface-level answer from an engineering answer.